Hello, Algebra Tutoring students, Mrs. Leopold here, starting lesson 1 from unit 6 about parent and piecewise functions. Today you're going to see a whole bunch of parent functions, and your goal is to definitely, if we talk about a cubic function, you should know what the sketch of the graph looks like. A quadratic function, right, is your parabola. You should know what these graphs look like so you can graph them with transformations. So we're going to talk about parent functions, and then we're going to transform them. So the more familiar you can become with these functions, the better off you will be. So let's recall we've studied quadratic functions in Algebra 1. We've studied it a lot in Semester 1. So hopefully you're saying to yourself, okay, the quadratic function has a center at 0, 0. Then I go right 1, up 1, left 1, up 1, right 2, 2 squared is 4, left 2, negative 2 squared is 4. You could fill out this table if you want to, but you know me, if you're in my class, I try to avoid tables. I'm hoping you just understand the relationship, right? So negative 3 squared, if we went left and right negative, or if you went left negative 3 and squared it, we would go up to 9, right 3, square it, would be positive 9. So this is your parabola. It's called a quadratic function. Sorry, a little rough here on my sketching, apologies. So how are g of x, the square root function, so this is called a square root, right? Sometimes we just do square root like this, a square root function. So what happens here? Well, if we take the square root of a number, right, g of 1, let's say, well, square root of 1 is actually 1. 1 times 1 is 1. So how about square root of 0? Square root of 0 is 0. So that's also a point on there. What if I put a negative 1? Well, I can't take the square root of a negative number, so this value does not exist. Okay, well, let's try a different value. How about 4? I'm choosing 4 because 4 is a perfect square. The square root of 4 is 2. So when I plug in 4, I'm going to get 2. Can I plug in negative 4? No, we just said the square root of a negative number does not exist. So far I have 0, 0, 1, 1. I go to the right 4, up 2. And then hopefully the next number you're saying that would make sense would be 9, because the square root of 9 is 3. So I would go to the right 9, up 3. And this is all we're going to get when we graph the function of the square root of x. So do we have any values down here in the negative region? No, we don't, because we can't take the square root of a negative. So we don't have any values over here to the left, and we don't have any negative y values, because when you take the square root of a numerical value, you only get positive results. So your square root function, we call this for both functions, this is the vertex, right? Right here, that's the vertex of the parabola, but of the square root function, that's also the vertex, and it goes only to the right. Now, hopefully you're looking here, and you're saying to yourself, hey, wait a minute. These ordered pairs have a lot of similarities. They are just switched. So if they're switched, then we call those inverses of each other. So these two graphs are almost inverses of each other, except if we want g of x to be the inverse of f of x, we would have to limit the domain of this function to only be greater than 0. Okay, but a parabola doesn't have a limited domain, but remember when we did have to limit it so its inverse was a function? Well, that's going to come back up in this unit. And we'll talk more about that as we continue through the lesson. So again, if we limit the domain of f of x, we say the domain only goes from 0 to infinity, so we're only looking at this right-hand side, then we would have f of x and g of x would be inverses of each other. Okay, moving on to a cubic function and a cube root. Again, understanding that f of x here, that's a cubic function, that's what we would call it, and g of x over here is the cube root, right? So this indicates that we have the cube root. So how do these two functions relate to each other? Well, a cubic function, maybe you've never graphed before, or if you have, you haven't really recognized where its center is, or different parts that we call it. So I would say we're going to start with some negative values, and then we're going to go to some positive values and see what happens. So negative 3 cubed, well, that's negative 3 times negative 3 times negative 3, which is negative 27. Okay, that number's too big because it's off the grid. How about negative 2? And negative 2 cubed is negative 2 times negative 2 times negative 2, which is negative 8. So if I went left 2, I would go down negative 8. So that would be that point there. If I cube negative 1, that's negative 1 times negative 1 times negative 1, which is negative 1. So there's that point there. If I cube 0, 0 times 0 times 0 is 0. 1 cubed is 1. 1 times 1 times 1 is 1. And 2 cubed, oops, is 8. 2 times 2 times 2, that's 8. So if we connect these with a smooth curve through there, then this is your cubic function. Now notice, your quadratic had that 1 to 1, 2 to 4 relationship. Here, this we call that our center. And it has a 1 to 1 because 1 cubed is 1, and then 2, and 2 cubed is 8. Or you go left 1, down 1 because negative 1 cubed is negative 1, or left 2, down 8 because negative 2 cubed is negative 8. Now what happens when we do the cube root function? Well, hopefully you're saying to yourself, because of the previous example, that, hey, potentially these are inverses of each other, which means perhaps we're going to switch these ordered pairs. I need to have a perfect cube that I put in for x, right? So 0 is a perfect cube. The cube root of 0 is just 0. So this point is also on the cube root of x. 1 is a perfect cube. The cube root of 1 is 1. So this point is also on there. Negative 1 is a perfect cube because negative 1 times negative 1 times negative 1 is negative 1. So this point is on that graph. And negative and positive 8 are my other two values. This cube root of negative 8 or the cube root of positive 8, what number times itself 3 times is going to give us negative 8? Hopefully you're saying to yourself that's negative 2. The cube root of negative 8 is negative 2. Negative 2 times negative 2 times negative 2 is negative 8. So I go to the left, negative 8, and down 2. So this is a point on the graph, and then I go right 8 because the cube root of positive 8 is positive 2. So this time, it's a similar looking graph to the cube, except it's on its side. So again, these are inverses of each other. Why? Because their x and y coordinates from f of x switched to their opposite and became y comma x. The other thing you might recall about inverses is they're reflective, graphically, they're reflective over the y equals x line, right? And if you folded your paper down that green dotted line, the purple and the blue graphs would line up on top of each other. So again, if you have like a function that's a cubic function, you should be thinking to yourself, oh, that's a graph that looks like this. If we say, hey, you have a function that's a cube, you should be thinking to yourself, oh, that's a graph that looks like this. So you know these are called the parent functions. This point right here in the middle is the center, and then we just have some kind of relationship from that center moving right and left or up and down a certain amount of spaces. And again, I'll talk about that as I go through more complex questions later. Next, we have our absolute value function. You've studied absolute values in Algebra 1. You should have graphed them as well. Recall that an absolute value of a number is the distance from that number to 0. And so when we're talking about the distance, if you look at a number line, right, this is 0, 1, 2, negative 1, negative 2. When we're talking about the absolute value of negative 2, we're talking about the distance from negative 2 to 0, and a distance is always a positive result. The negative sign is indicating a direction. So this is 2 units away, so the distance between 0 and negative 2 is 2, just like the distance between 0 and 2 is also 2. So you always take the positive value when you're doing an absolute value graph. Therefore, if I choose some negative and positive, so negative 2, negative 1, 0, 1, and 2, this just is the absolute value of negative 2, which is the distance we said is positive. It's just 2. This is just 1. So the absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. So hopefully you're recalling that an absolute value graph is just going to be a V, right? Cutting straight through the first and second quadrant. We call this point down here the vertex. And again, it has a V shape. So if we're talking about an absolute value function, hopefully you're immediately thinking, oh, it must be a V, right? Also, this absolute value function, it's reflective over the y-axis. So later on, we'll talk about the inverse, or actually next lesson, we'll dive into absolute values a little bit more. So the next part of this lesson is really just, again, trying to get you to familiarize yourself with the graphs of the different parent functions. These are the most common ones. These are the ones you're going to see. To be honest, this linear one, we're not going to do much with that. You studied it so extensively in Algebra 1. We're not going to worry about that, but of course, m is your slope, b is your y-intercept. You know, if you want to recall what the linear function represents, m is your slope, which is your rise over your run. And then b is your y-intercept. Quadratics we studied extensively. Remember, this right here is called the vertex. The vertex, of course, then is represented by your HK. Your A value is your vertical dilation, how much is being stretched or shrunk vertically. Remember, we talked about the 1 to 1, 2 to 4 relationship, right? You go right 1, square it, go up 1, go right 2, square that value, go up 4 from the vertex. And then if there's some kind of vertical impact, we stretch it or shrink it. For your cubic function, right now you can see the parent function looks like this. The important point is this point here. We call that the center. So this time the center is h comma k. A still represents your vertical dilation. So typically from the center, we go right 1, up 1, because 1 cubed is 1, and right 2, up 8, because 2 cubed is 8. Or we go left 1, down 1, because negative 1 cubed is negative 1, or left 2, down 8, because negative 2 cubed is negative 8. So the shape, the general shape of a cubic is like this. For your exponential and your logarithmic graphs, we just studied those. So exponential, this is your, has a horizontal asymptote. This is the, initial value, I guess we might call it. It's associated with your A, if there's a stretch or not. We have a base, which is the very next point, how far away it is from your asymptote. H comma K is just indicating where your new X and Y axes are, how far you move your Y axis, how far you move your X axis to relocate kind of that anchor point. Your logarithm has a vertical asymptote, right? We still have a base, which is associated with that distance away from your vertical asymptote. We have your stretch value, which is just this anchor point here, that initial value. Again, moving our X and Y axes. Yep, and then we have our absolute value graph. So remember, your absolute value graph has the shape of V. We call this point down here at the bottom the vertex, and your vertex is represented by H comma K. And this A value is also associated with your vertical dilation, which is your vertical stretch or shrink. And really, one thing that will be helpful actually is the right-hand side of your vertical asymptote. Whatever that A value is, that's associated with your slope. And it's for the right-hand side of the graph specifically. And then once you get that slope, you can reflect it through to the other side and get the other side to see what it looks like. But the A value indicates the slope, which is your rise over run, and I'll show you that later. And that is only on the right-hand side of the graph. And again, we'll look at that later. And the newer graphs probably are the square root and the cube root function. So your square root function is going to be just half, right? So this is called the vertex right here. And we only do the upper portion because we need positive values underneath the square root symbol. We call this the vertex, so H comma K is still your vertex, and the A value is still associated with the vertical dilation, which is your stretch or shrink. And of course, you can reflect it if it was negative over the x-axis. Your cube root, we call this the center. So h comma k is your center, right? So this is your center point. And again, if you're cube rooting, you're going right 1, up 1, but you're going right 8, up 2, because the cube root of 8 is 2, or the cube root of negative 8 is negative 2, or negative 1, negative 1. So those are your kind of crucial points you're going to graph. A value is still associated with your vertical dilation, your stretch or shrink vertically. And the reciprocal function we will study in pre-calc, so not to worry, but it would look like this if your variable was in your denominator. So let's jump in. We have example 1 here. It says, follow these steps to write an equation for the graph g of x. So first, we want you to look at that. We want you to be able to look at that picture, and first you're going to say to yourself, okay, what type of function is it? You can go back through those 9 functions we just looked at and say to yourself, what does this look like? What does that graph look like? And hopefully you're saying to yourself, oh, that looks like a cubic function. It looks like the parent function that's x cubed, right? And so once you figure that out, that's the first step. And then you're going to kind of say to yourself, okay, well, my center is usually at 0, 0, but instead it got moved to the right 4 and down 1. So my new center is to the right 4 and down 1. Well, how does that get impacted in your transformation equation? Well, the transformation equation, if you look, and I'm using g of x, this is a g of x up here, you have your stretch value a, which we're trying to find, and you have your center value h and k. So we're trying to fill in for a, h, and k. And I just said by moving the center to the right 4, down 1, this is your h and your k. So h is equal to 4, so now I have g of x equals to a, and I have x minus, I put in my 4, cube it, and my k is negative 1, so I put in minus 1 for my k. Finally, I have to find the a value, so I can pick any point that is not the vertex or the center, so I don't want to pick this point here for negative 1. I can pick this point here, which is 6, 1, or I could pick this point here, which is 2, negative 3, either of those points to find your a value. So I'm going to say g of x equals a times x minus 4 cubed minus 1. I'm going to pick the two positive values. So when x is 6, y is 1. So this is y value. So when y is 1, x is 6. So order of operations says I'm going to add 1. Move that over. I'm trying to isolate my a, so I add my 1 first. Then in my same step, I'm going to subtract 6 minus 4 is what? That's 2. I get 2 cubed. 2 to the third power is 8. So I divide by 8. So a is equal to 1/4. So my final step is to put it all together. My a value is 1/4. My h and k, right, are positive 4, negative 1. And so this is my final answer to represent that graph over there on the right. Now, if you wanted to try to use the 1-to-1, 2-to-8 ratio, right? So remember I talked about that earlier. Let me erase all this over here. So typically, from a cubic function, we would go to the right 1, up 1. So that's a fraction. That's not very helpful. We're not going to be able to figure out what that fraction is because we don't know this exact value. But if we went to the right 2, we went up 2 units. When we went to the right 2, we went up 2 units. Typically, when we go to the right 2, we go up 8 units. So whatever you're supposed to go up is in your denominator, and whatever you actually go up is your numerator. So you only went up 1/4 of the distance, which is how we got that vertical dilation of 1/4. So if you don't want to do all of this math work over here, and you can figure it out graphically because these points are exact and you understand this ratio we can figure out, the actual distance that you moved versus what you were supposed to move, then you could figure out your a value without actually plugging in the points. So up to you. Ask your teacher if you want more information or come see me and I will certainly help you through that if you want that extra help. Okay, moving on to these two questions. You can stop and pause and try them on your own, or you can do them along here with me. But first, I would say I'm hoping you're going to look at this graph right away, and you're going to say the only graph that has an endpoint and goes in one direction only, up or down, is your square root function. So hopefully you're saying to yourself, oh, this must be a square root function. And then over here, if it looks like this, hopefully you're saying, oh, that's a cubic that's been reflected. So we have a cubic function for letter B and a square root function for letter A. And if you have that in your mind, it's going to help you figure out, how to get started. So for a square root function, we have a vertex. So this is our vertex right here, and our vertex is left 4, down 6. So if we have our function, it's a times the square root of x minus h plus k. So I can fill in -4 and -6 for my h and k. So my next step is a times the square root of x plus 4, because I have to subtract a -4, and then I get -6. So the last thing I have to do is actually calculate my a value. So in order to do that, you can take this point here, which is 0, 2. So that means when y is 2, x is 0. So I plug in 2 for y. I plug in 0 for x, and I calculate. So first thing, hopefully you're saying, oh, I have to add 6 to both sides. So I get 8 equals a times the square root of 4. What is the square root of 4? The square root of 4 is 2. So I get 2a equals 8, therefore a equals 4. So that tells us what a is. So now my final solution for the square root function here is 4 times the square root of x plus 4, and then -6. Now, if you wanted to try to do it without, oops, wrong thing there. If you wanted to try to do it without actually calculating a square root function, well, when you move to the right, you typically move up 1. Well, they didn't give us a point here. We move to the right, we typically move up 1. It looks like this is our point. So instead of going up 1, we went up 1, 2, 3, 4 units. So the actual distance we went up versus the real distance we were supposed to go up. So it looks like a is 4. Let's double check it with this point. When you go to the right, 1, 2, 3, 4 units, the square root of 4 is 2, so you're actually only supposed to go up 2 units, but instead I went up 2, a second group of 2, a third group of 2, a fourth group of 2, or in other words, I went up 8 units when I was supposed to go up 2 units. Again, gives me an a value of 4. So I could have done it without actually plugging in, but plugging in might be a better bet. All right, let's look at letter B. Letter B is a cubic. Where is the center of the cubic? Hopefully you see that's right here. Your center is to the left 3 units, up 2 units. And so my cubic function is a times x minus h cubed plus k. So I'm going to plug in for my h and k according to my center. So I plug that in, I get f of x equals a times x plus 3 cubed plus 2. Then I'm going to take this point down here, which is -1, -6, and I need to plug it in. -6 is my y value, -1 is my x value. I'm going to plug that in to get my a value. So -6 equals a times -1 plus 3 cubed plus 2. Order of operations, so I have to subtract my 2 first. So I get -8 equals a. I'm going to add this. What is -1 plus 3? That's 2. So I have 2 cubed. 2 cubed is 8. So -8 equals 8a. Therefore, a equals -1. So I can see here I went right 1, down 1 instead of up 1, right 2, down 8 instead of up 8. So I flipped that graph over the x-axis. So I get a -1 in front and then my x plus 3 cubed plus 2. Again, if this is going too fast or you're having any difficulties, please make sure you go ask your teacher follow-up questions. Okay, letter C and letter D. I'm hoping you're looking at those graphs and you know what the parent function is right away. So the parent function for this graph, I hope you're saying, oh, that's the absolute value of x. The parent function for this graph, I hope you're saying, well, what is it? It's on its side. This is, oops, the cube root of x. So the cube root of x. Now that you know the parent functions, you can then look at the vertex or the center and then use a point to calculate the a value. So you can try that on your own, right? Or you can go ahead and do it here along with me. But if you try it on your own, go ahead and pause now. Okay, so I go to the right 3, down 6, so that's my vertex. So I'm going to say, okay, I have my stretch value of a, it goes to the right 3 and down 6. So that's the first thing I start with. Then if I focus on the right-hand side of the graph only, I just look at the slope, and the a value is the slope. So from the vertex, I would go rise over run. I went up 2 units, that's positive. Right 3 units, that's positive. So my a value is just simply 2/3. So my function is 2/3, absolute value x minus 3, and then minus 6. For letter D, again, pause. If you want to pause on your own, you know it's a cubic function. Otherwise, you can do it here with me. First, I'm looking at my center. My center is -1, 4. So I'm going to plug that in. I'm trying to find my a value. I don't know what it is, but I do know, I have the cube root of x plus 1. So I'm taking the cube root of x plus 1, and then I add plus 4 out there. So I have to find my a value. How am I going to find my a value? Or I'm just going to take a point on the graph. This point is 7, 5. So when y is 5, x is 7. So I get 5 equals a times the cube root of 7 plus 1, and then plus 4. So I subtract 4 from both sides. So I get 1 equals a times the cube root of 7 plus 1, which is 8. Well, the cube root of 8 is what? What times what times what will give us 8? Hopefully you're saying 2. 2 times 2 times 2 is 8, so the cube root of 8 is 2. Therefore, a equals 1/2. Put it all together just by substituting in our a. My function is 1/2 times the cube root of x plus 1, and then outside of that cube root, I have my plus 4. And that's it. Okay, next one. Example 3. Hopefully you see this is a square root function, and in your mind, I'm hoping you're saying to yourself, okay, square root function looks something like this. And I'm going to manipulate that square root function by relocating this vertex. Remember, this is the vertex. This is the parent function. And if you understand the parent function, then you know you can shift your vertex to the left 5 and down 4 according to these 2 points right here. So I go left 5, down 4, and this is my new vertex. From there, I typically go up 1, or right 1, up 1, and then I go right 4, and the square root of 4 is 2. So I do 1 to 1, 4 to 2, but now I'm stretching it 3 times higher vertically. So instead of going right 1, up 1, I have to stretch that 1, 2, 3 times higher. So my point should be right here. Then I would go right 4, 1, 2, 3, 4, and the square root of 4 is 2, so I would go up 2 units, but I'm stretching 3 times higher, so that's 1 set of 2, 2 sets of 2, 3 sets of 2, so I think my point should be up here, because I'm vertically stretching 3 times higher. So let's double check that by using the table of values. I don't always want you to use the table of values, but sometimes it's helpful. One of the things that is helpful with our table of values is to try to get perfect squares underneath, oops, didn't mean to do that, underneath your radical there. So, sorry, I'm going to put that back up. That's my vertex. So I want to get a perfect square of 0, a perfect square of 1, a perfect square of 4, or a perfect square of 9. So how could I do that? Well, I need to pick values that are going to give me that perfect square. So what value of x would make this inside become 0? Well, hopefully you're saying to yourself, and that's -5, because -5 plus 5 is 0. The square root of 0 is 0. 3 times 0 is 0, and 0 minus 4 is -4, and that is how we got to the vertex point right here. Then I would go with a 1. How can I get a 1 underneath that radical? What does x have to be to make that a positive 1? Hopefully you're saying to yourself -4, because -4 plus 5 is 1. 3 times the square root of 1 is 3. 3 minus 4 is -1. So I have an ordered pair of -4, -1. That's this point here. I had already predicted that was going to be a point on the graph. Let's look at our next one. How could I make this a perfect square underneath the radical? How could that become a 4? That means x would have to be -1, because -1 plus 5 is equal to our 4. The square root of 4 is 2. 3 times 2 is 6. 6 minus 4 is 2. And so this is an ordered pair of -1, 2. So I go left 1, up 2. There's my third point. And a fourth point, if I wanted to make that 9, well, 9, I would go to the right 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what is the square root of 9? It's 3. So I go up 3, but I'm going to stretch it 3 times higher. So I go up 1 set of 3, 2 sets of 3, 3 sets of 3. So I'm predicting that's what my point's going to be, and this is what my graph is going to look like. Well, let's see if that's true. How could I make underneath the radical equal to 9? That means x would have to equal 4. 4 plus 5 is 9. Square root of 9 is 3. 3 times 3 is 9. Minus 4 is 5. So right 4 up 5. So I was correct. So you don't need to use your table if you understand that relationship that I've tried to explain over here. If not, please ask your teachers. They'll be happy to help you. Okay, I would try this on your own. Go ahead and pause. You have a cube root. Hopefully you're saying to yourself that a cube root function looks like this, right? If you look at the parent function, this is what it's going to look like. Usually you go to the right 1, up 1, to the right 8, up 2, or left 1, down 1, or left 8, down -2. Because the cube root of 8 is 2, the cube root of -8 is -2. You can see you relocated your center. This is the center here at the origin. We relocated it to the left 1, down, or sorry, up 3. So you can try to fill out this chart, or you can try to do the relationship that I described in previous examples. So go ahead and pause and try it on your own. All right, did you get this picture? Does your graph look like this? So first we relocated, we went left 1, up 3. That's my center point. Then I would typically go right 1, up 1, but I had to stretch twice as high, so I went up 2 units instead. Then I would typically go right 8, up 2, but instead of going up 2, I had to stretch it twice as high, so I had to go up another 2 to go up 4 units instead. So if I did the table, I got those corresponding points. If you didn't do the table, then you did what I'm doing, which is left 1, stretch it twice as far down, left 8, instead of going down 2, we went down 4. So regardless, your graph right there is what you should have had. If you didn't, make sure you're checking in with your teacher or seeking out that assistance early. Again, this absolute value, I would pause and try it on your own. Like hopefully you're saying to yourself, an absolute value, what is that going to look like? That's going to be a graph that's a V with the center or the vertex, sorry, at 0, 0. If I have this negative in front, how is that going to impact my absolute value? Hopefully you're saying that's reflection over the y-axis, or sorry, the x-axis, so it's opening down instead of up. What's the impact on the center, or sorry, excuse me, the vertex? It's going to be shifted to the right for down 1. So you can pause now and do it on your own, or you can follow along with me. Excuse me. So I go to the right for down 1, and from there, I'm going to go the slope. Remember, I do the slope on the right-hand side only. So I do the slope on the right-hand side. So the slope is -3/2. A negative slope looks like this. So I'm going to go from this vertex point down 3, right 2, down 3, right 2. This would be half of my absolute value. Because my vertex is right here, I reflect it over that vertical line going through the vertex, and that would be the other half of my absolute value function. So this is what your graph would look like, right? It's negative stretch value, so it's opening downward because it's reflected over the x-axis, and then that 3/2 is indicating the slope. Example 6, our last graphing example. It's a cubic function, right? So hopefully you're saying to yourself, it's a cubic function. What does the graph of a cubic function look like? Hopefully you're saying it looks something like this, where this is the center. So I'm relocating my center, and I usually have that 1 to 1, 2 to 8 relationship, 1 to 1, 2 to 8 relationship. But this time we're going to smash it. It's going to shrink vertically instead of stretch vertically. So I'm going to half that vertical distance. So go ahead and pause, try it on your own, and come back and see how you did. All right, does your graph look like mine here on the right? If you used a table, your table should have looked something like this. I didn't use a table, of course, when I graphed it, but I showed you both just in case. But what I did was I said, here's my center. I'm going to go to the right one. Typically, I go up 1, but I'm going to shrink that to half its height. So instead of going up 1, I go up half. When I go to the right 2, I typically go up 8, but I shrunk that to half its height, so I only went up 4. I repeat that the other direction, left down a half, left 2, down 4. And so here are my points making this the graph of my function. And if you did it algebraically, I would say plug in, you start with your 2 points that make up the vertex, then plug in the 2 points to the right of the vertex, the 2 points, 2 x coordinates to the right, the 2 x coordinates to the left to get your results. So you would have your points to put on your graph to help you with the shape. So there you have it. So again, start with your vertex. If it's a 3, go to the right of the vertex, go to the left of the vertex, go 2 to the right of the vertex, 2 left to the left of the vertex, plug them in, see what you get. Okay, finally, we're doing some algebra here at the end. Our first two examples from example 7 are to find the inverse. And remember, to find the inverse, what do? We switch the x and y, we solve for solve for y, and then we have to replace y with f to the -1 of x. So my y value becomes my x value becomes my y value. I resolve for y, and then I replace y with f to the -1 of x. So what do I do first? I add my 6 to both sides, so I get x plus 6 equals 2 times y plus 4 cubed. Then I divide each side by 2, so I have x plus 6 divided by 2 equals y plus 4 cubed. Now, how do I undo the cube of a function? Because I'm trying to isolate y, so I need to undo this. I need to get rid of these parentheses. So I'm going to cube root both sides. So cube rooting a cube makes us just have y plus 4 by itself, because those two operations are inverses and they undo each other, like addition, subtraction, or multiplication, division. So on my right-hand side, I have y plus 4. On my left-hand side, I have the cube root of x plus 6 divided by 2. So my last step, if you're in my class, you know I always combine. I replace my y with f to the negative 1 of x in the same step as moving 4 to the other side. So I'm going to subtract 4, move it to the other side, and I'm also going to replace y with f to the negative 1 of x. So this is the inverse function of my original f of x. So the inverse of a cube is a cube root. The inverse of an exponential is a logarithm. The inverse of a square root is a square, or squares and square roots, logs, exponentials, cubes and cube roots. So pause and try this one on your own. Switch the x and y, solve, and see what you get. And we'll talk about it, unpause when you're finished. Check. All right, did you get this equation? You either got f to the negative 1 of x equals 16 times the quantity of x minus 3 squared minus 2, because you had to square the 4 and square this parentheses. Or perhaps you distributed 4 times x, 4 minus 3, and you got 4x minus 12, and you squared that, in which case you would have gotten f to the negative 1 of x equals 4x minus 12, the quantity squared, minus 2. Those are the same answer. We would accept both of them. They're fine. Actually, they're not fine. They're both wrong, but we're going to talk about why. And you can see this stop sign right here, the stop and think. Maybe you already figured it out, but let's think of this graphically, right? If we had that g of x, that g of x is a square root function. So hopefully you're saying to yourself, okay, a square root function would be a vertex rooted at 0, 0, opening that looks like this. But I have a new vertex that goes left 2, up 3. So I go left 2, up 3, and it's going to shrink vertically, but regardless, it's still going to open something like that to the right. But I just relocated my vertex. Now, if I look at a parabola, either of these parabolas, they have a vertex of 3, negative 2, right? That's my vertex here. My vertex, the same, would be 3, negative 2. So I go to the right 3, down 2, because they're inverses. I have to switch those ordered pairs. But it's a positive stretch value, so it's going to open upward. But are those inverses of each other? Is that the proper reflection over this y equals x line? And hopefully you're saying to yourself, oh, right, no, I can't have both the left-hand side and the right-hand side of the parabola. I must only have the right-hand side because this is the upper portion of the parabola on its side, so I can only do the right-hand portion of the parabola. So I have to restrict the domain. So both of these, I have to go from 3 to infinity only. I have to go from 3 to infinity only. So it's essential that I restrict the domain and I only go from 3 to infinity. And now I have a proper reflection over that y equals x line. So you must restrict the domain in order to get the answer correct. And we will do more of that in our next lesson, in lesson 2. We'll be bringing that back for the absolute value as well. Finally, our last example is to determine using function composition if the two are inverses of each other or not. Function composition, to remind you, says that f of g of x equals g of f of x equals x. So if f of g of x equals g of f of x equals x, then we know that these are inverses of each other. So when we take this entire function and replace it into the x for f of x, if we get x as a result, then we also have to take this entire function and replace it into x, into g of x, and if we get x as a result, then that proves they are inverses of each other. So let's start with one. We're going to do f of g of x, and we're going to see what happens. So I'm going to take the function f of x, and I'm going to replace this entire thing into the x. So I left this big blank spot because I'm going to replace that with the cube root of negative x minus 2 plus 3. Right, so I took this x, I put the minus sign down here, took the x, replaced it with my g of x, so that's what this says to do. We're replacing g of x into x. And then I'm going to solve or simplify algebraically. So what do we do? What do we see? Well, we have a plus 3 minus 3. So those are going to cancel each other out. Then I'm going to cube a cube root. So how do I cube a cube root? Well, those cancel each other out. So I have a negative on the outside, and I'm just going to get negative x minus 2 on the inside, because this cube and this cube root cancel each other out because they're inverses of each other. So I just get negative x minus 2 inside that parentheses, and then I have a plus 2 out here. But this negative sign makes us distribute this, so be careful, you have a minus 1 in here. So negative 1 times negative x is positive x, negative 1 times negative 2 is positive 2, and x plus 2 is not x, it is equal to x plus 4. So if f of g of x does not equal x, it equals x plus 4, therefore g of x and f of x are not inverses of each other, right? So f of g of x does not equal x. You don't even need to check g of f of x, but it also doesn't equal x. It's even more complex and more complicated of an answer, but they are not inverses unless, if you would have gotten that equal to x, you would have also had to prove it the other direction, and you would have had to end with this statement here and say they are inverses because of that. Again, we'll do more of that in your homework. You can ask questions of your teacher to see if you have any questions. Yeah, follow up. All right, bye. Sorry it's so long. See ya.